Hello, this is Mr. Cook, and I'd like to welcome you to our webinar about perpendiculars and bisectors, and we're going to be talking about perpendiculars and bisectors of triangles. So first, we're just as the in, I'd like you to try to find the midpoint of BC, and so you can pause it and work on the problem. If not, we're going to move along and just recall that down here is the midpoint formula, and the midpoint formula is add the x's together, divide by 2, add the y's together, divide by 2. The midpoint formula gives us an address of where the midpoint is, so we'll go ahead and find that. So to find my x values, I'm going to take the 0 and add on -2 and divide it by 2. And for my y values, I will take 4 and add on 0 and divide by 2. And when I do those, if I just reduce these, I end up with -1 as my midpoint and 2 as the y value. So -1, 2 would be the address of the midpoint of those lines. So we're probably going to use that today as we move along. So we're going to move into some theorems. And so if a point is the perpendicular bisector, we're going to talk about the perpendicular bisector theorem. And basically the perpendicular bisector theorem says if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So we're basically saying this segment right here is the perpendicular bisector. You can see that it's perpendicular bisecting the segment AB, where it is a 2 equal pieces. So it's perpendicular the right angle and bisecting, cutting into 2 equal pieces. Then we know that the segments out here are going to be equidistant from, they're going to be equidistant. They're going to be the same length. So CA will be equal to CB. So we're saying that if CP is a perpendicular bisector of AB, then this point, any point on the perpendicular bisector, is the same distance to A as it is to B. So I could have picked a point right here, and that if draw the line in there, these two little red, if I could draw straight lines, these two little red lines should be equidistant from the point, from this point down to A would be the same as it is from here to B. All right. So then we have the converse of this, which is just the reverse. So if a point is equidistant from the endpoints, equidistant. Sorry for the bad handwriting here. I'll try that again. Equidistant. I don't know what's going on with the handwriting here. Equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So we're basically saying that if we know point D is the same distance to B as it is to A, then it is on the perpendicular bisector. So if DA is equal to DB, then we know that we are on the perpendicular bisector of the segment. Hold on here, let's try this again. DA, DB. Alright, so if those are equidistant, then we know that if they are the same, then we know that we're on the perpendicular bisector. That's what the converse says. We also have an angle bisector theorem, and the angle bisector theorem says if a point is on the bisector of an angle, so then it is equidistant from the two sides of the angles. So sides of the angles. So it doesn't matter if I just pick up, here's the angle bisector. AD is my angle bisector. So then I know that DB and DC are equidistant from the sides. Now we always measure to the sides at a 90-degree angle, so we know that these guys will be equal. So if angle BAD is equal to CAD, then DB and DC are equal. Okay, that's what we're telling us. And the point could have been here, but the thing is, we still have to have 90-degree angles to the sides because we always measure at 90-degree angles. That's how we find length, so those pieces would be equal to one another. Okay, so you just know that. You're always looking for the right angles. So then we, of course, have the converse of this that says if a point is in the interior of the angle and is equidistant from the sides, of the angle, then it lies on the bisector of the angle. So if we know that BD is equal to DC, then we know that the angle is bisected. Okay, and so you can see it's basically looks like the same drawing. So if we know that these guys are the same distance and we have right angles, then we know that D is on the angle bisector. Okay, so those are things that we need to know for today. If you need to pause them to write them down, please do. All right, so now we're going to do a couple examples. And so our first example says find the length of AB. Well, hopefully you notice, so pause it if you want. If not, here we go. Hopefully you notice that BD is a perpendicular bisector of AC. One, I know it's perpendicular because there's a right angle marked there. And two, I know it's a bisector because these guys are marked the same. So DC is equal to DA. So knowing that, then by our perpendicular bisector theorem, we know that these two sides, AB, is equal to BC. So we first need to know that BD is perpendicular to AC, and we need to know that AD is equal to DC. And once we know that, then we can say, if this is true, then we can say that AB is equal to BC. And that's by the perpendicular bisector theorem. And that's the key piece of information, is that these two guys are equal. So now if we want to find the length of AB, we have to first find out what x is. And since we know those two pieces are equal, we're going to set them equal to each other, follow our steps of algebra, and find out that x is equal to 3. So knowing that x is equal to 3, if I want to find AB, AB is 5x, so AB comes out to be 5 times 3, which is 15. So is that the same for BC? Yes, it is. So AB is equal to 15, and so is BC. And if we put 3 in there, you can see that it's 4 times 3 plus 3 should be 15. So then, talking about perpendicular bisectors, perpendiculars and bisectors, it says, is there enough information to conclude that C is on the perpendicular bisector of AB? Well, what did we say? What the converse said? The converse said, if AB is bisected by a line, which it is, it's bisected, cut into two equal pieces, and these two sides are equal, then yes, we are on the perpendicular bisector. So C is on the perpendicular bisector of AB. All right, so then over here, this is no, because even though we know that AP and BP are the same length, do we know that CP is at a right angle? Well, the only way CP is at a right angle is if CB and CA are the same length. Because as you may note, you could draw a line like this. And so here's my counter example to this. If I draw something that does this, okay, so let me draw a triangle. So then this blue line that I'm going to draw in here is the bisector. So that's cutting the pieces in half. Are these two sides the same? Not necessarily. And so that's what's happening in this drawing. As soon as you make these two sides the same length, then that line ends up being a perpendicular bisector. So just remember that as we go through this. Okay, so now they're asking us, is BD equal to CD? So this is talking about the angle bisectors, and so we got to look at this. Starting with this one, well, we have a right angle here, and we have a line. Well, how would we know if these guys are the same length? The only way this would be at the same length is if, like, these two sides were the same, or if the angles were the same. Can I draw a right angle to another triangle? So let me give you a counter example. Of the triangle is going to look kind of similar to the last one I drew. I can draw, oh, let me try that again here. If I could draw straight lines here. I can draw a triangle that looks like, whoa, that's a terrible triangle. Let me try again. Let me just see if I got a triangle tool that will work for me here. That one will work, maybe. We'll try it. No. Well, that'll work. All right, so if I have a triangle that looks like this, I want it to sit like that. This is what I was looking for. So I have a triangle that looks like this, and can I draw a line that is perpendicular to the opposite side and not be not have those two sides equal? Well, there you go. So that could be what's happening. We don't have nearly enough information in this problem to figure out if they are equal to each other. So then, over on this example, you'll notice they told us that these two angles are the same, and that this line is being drawn, these lines are being drawn at a 90-degree angle. So that means that they are talking about the length. So BD and CD, since they're on the angle bisector by our angle bisector theorem, these guys have to be the same length. So this one is yes, this one is no. So moving along now, we are going to figure out which problem this is. And so if we look at this, we're trying to find the value of x. So I'll give you a second to kind of look at it. You may notice that this one is talking about an angle bisector because we know that these two lines are the same length and they're measured at a 90-degree angle. So if they are the same length, then that would mean that this angle would be equal to that angle by our converse of our angle bisector theorem. So that means that I can set, if I need to find x, I'm going to set 7x equal to 3x plus 16. So now solving it algebraically, move my x's to the same side. I end up with 4x equaling 16. If I divide by 4, x comes out to be 4. And that's really all I needed to do. But I'm going to do a quick little check to see if I'm right. And so for this angle, if I do 7 times